Good morning, everyone. Today, I'd like to share a little bit of information on this lab that we're going to be going through today. Let me address the elephant in the room. There are no good virtual labs for kinetic friction. There are a few applets that can be looked at to describe kinetic friction and static friction, but overall, this is a lab that really requires hands-on experience and a application to the physics that we've discussed thus far. And that's why we're doing this in lab this week. Kind of a dual schedule, if you will. So as a reminder, if you're in group A, you will be coming into lab from 3 to 4:20 to ask questions and collect data. That is really the primary motivation for your attendance in lab today, is to just get questions answered and to complete the lab experiment and getting your data as quickly as possible. The analysis portion of this lab can be done at home in your own leisure time. The group B will come in at 4:30 and will leave at 5:50, giving them enough time to do the same thing. Those of you who cannot come to lab today, which I realize there's a number of you, rather than doing this lab this week, we're going to write up a brief report on the physics of the mystery box that is in the Forces in Motion applet on Moodle in the course. So basically, you'll be doing the same thing I did in class with the motion and forces applet on the internet, but this time you'll be looking at finding the kinetic friction of the mystery block in that set. So one of the first things you'll do is you'll just kind of get a hand on the software, and there'll be an instructional video for that produced later today. But basically you'll go through a tutorial, then you'll do a couple of analyses on the crate in the refrigerator or the file cabinet in that applet, and then you'll look at determining the kinetic friction coefficient of the mystery box, and you'll write up a brief report on that and hand that in for your lab this week. Now, I only offer that to a few students, the ones that can't actually make it, because it is the bare minimum of what needs to be done this week. There's actually a lot more that is more sophisticated and more instructional when you come into a lab on hands-on. So let's just briefly look at the procedure for this week. So this is for students that are coming into lab today, not the ones that will be at home this week. I want you to read through this entire introduction. Make sure you understand it. I want you to also read through this section on free body diagrams. Make sure you run through it all completely. Make sure you understand these equations. How do we derive them? We've done this in class a number of times. And then finally, practice coming up with equations of motion just like this in this first example, using different scenarios than are presented before. Then go through and have a good look at the section on the experimental setup. Essentially what you'll do in lab is you'll have a block 1 being suspended from a pulley. So this is block M2 and this is block M1. The tension at every point along the string is identical, and this is what allows us then to calculate the equations of motion and determine the coefficient of kinetic friction. So your setup will look something exactly like this. Notice that this block will be accelerating downward because it's slightly heavier than this block here. Not significantly so, but just enough so that it begins to accelerate. That means that this block will accelerate towards the edge of the table as this one accelerates down. and because the tension is equal at every point along the string, we can come up with equations of motion that allow us to manipulate for tension and then set those two equations equal to one another and solve for this subject right here, which is the kinetic friction coefficient. So go through the derivation of these equations, make sure you understand each step, and finally the conclusion, which is this guy right here, equation number 6. The procedure in lab is very simple. The first time you do this lab, you'll be setting it up so that it looks identical to this, figure 1. Once you have that properly set up with the string attached, you're essentially going to start the Pasco system like we did last week for the free fall, and you'll be doing this in groups so that the data collection is efficient and quick. You'll input this information into an Excel sheet and it will automatically calculate the kinetic friction coefficient for you, as well as the average of that value and the standard deviation. For trial 1, you're going to orient the block so that it's on its largest surface area. Okay? And that way we can test a few things: largest surface area, smaller surface area. So the first trial, we will be the block on its side. And then you repeat the experiment after a number of trials with an added block on top. And then the third trial, the only thing you're going to change is, rather than being on its large side, you're going to orient it so that it is on its smallest side. And from there, you'll get 3 data tables with 10 data points each. Mass 1 and Mass 2 will not change once you've determined a good mass to accelerate the block. Pasco will determine the acceleration. You'll input that information here. Mass 1 and Mass 2 will be the same all the way down, and it will automatically in Excel calculate this mu value, as well as the average and standard deviation. Then you'll start over. You'll have Mass 1 of the block and Mass 2 of the other block. Mass 1 will be the total combination of 2 blocks on top of one another. Mass 2 will have to be re-evaluated in accordance with those masses so that it actually accelerates. Once you have that acceleration, you're going to do 10 data points again. From the time you start collecting data, M1 and M2 will not change in this table, only the acceleration may change very slightly, and you'll get a value from UK for each of these trials. Trial 3 will include doing this as the object is on its side. Once again, you'll determine Mass 2 that will accelerate the object, but once you have that good acceleration, you'll keep Mass 1 and Mass 2 the same in this table. You'll get acceleration, and it'll calculate for you UK, average, and standard deviation. That is pretty much all you need to do in lab today. Now, I should mention that once you have that, there are questions at the end you'll need to concern yourself with and answer. But once you're done with all of that, you have all your conclusions, you can go ahead and submit the lab here. You'll also want to complete Lab 4 quiz by the end of this week. Too many of you have been missing these, and as a result have received lower scores than you probably would have liked. Please do not do that this time. I am here to answer questions in lab today, but we need to be done by 4:20. I will be kicking you out, Group A, at 4:20, whether you're finished collecting data or not. So it's important that you do this quickly and efficiently, and I will not be taking up massive amounts of time at the beginning of class to make sure that we have done this. Instead, I will be going through the derivations of these equations in videos that you can then reference later on as you're writing up your lab report this week. That will be a very important matter come next week when you have to run an experiment of your very own. And because of that, I will try to allow as many students in as possible simultaneously, because you will not need the computers next week. Instead, you'll be basically coming up with a lab experiment that allows you to do everything by hand to determine the value of the coefficient of static friction. So this week is kinetic friction, next week is static friction. So go back to your notes and figure out what we did for those. That's all I wanted to share today. We'll discuss the bulk of this in lab, but I want you to have a heads up so that you are not completely confused. Make sure you come in at your allotted time, and make sure you've read the procedure and know what's ahead of you before coming in the lab today. That way you can ask deliberate, pointed questions. I will not be going through this in a hand-holding manner. We don't have the time for that. We don't have the space for it. And that's all I have. So I will see you in class and or in lab today. Thanks for watching.